On Friday, May 1st, a government climate chart ran out of room. NOAA's most trusted El Niño forecast model produced numbers so extreme the chart physically couldn't contain them. No press conference, no emergency alert. They just extended the y-axis to plus 4 degrees Celsius and kept going. What that chart is pointing at, plus 2.9 degrees of ocean anomaly by December 2026, higher than 1997, higher than 2015, equivalent to 1877, the El Niño that collapsed monsoons across 3 continents and killed somewhere between 30 and 60 million people. James Hansen says 2026 will be the warmest year in human history. The WMO is using the word unprecedented. The Met Office calls that premature, and NOAA, the agency whose chart just broke its own ceiling, hasn't used any of those words publicly. Not one. The model is screaming, the institutions are whispering, and the scientists most certain about what's coming are being the most careful about how they say it. So what's in that data that nobody will put in a press release? Stick around! Because the answer starts 300 meters below the surface of the Pacific Ocean, where the water is running 7 degrees above normal right now. The heat is already there, it's already moving. And it has been building since December of 2025 without a single headline. If this already has you asking questions, hit like and subscribe to the Skylab, because this story is nowhere near finished. The chart has already been redrawn once, the subsurface heat is still loading, the Kelvin waves are still stacking, and somewhere between the official language of cautious probability and a forecast median that has no modern precedent, there is a gap that somebody needs to keep filling in. That is what we do here. You are going to want to be here when the next update breaks. Now let us get into it. Part 1. The day the forecast broke its own limits. Something broke on May 1st, 2026, and most people had no idea it happened. It wasn't an earthquake. It wasn't a satellite failure. It wasn't a server going down somewhere in a government data center. What broke was something far quieter, and in some ways far more unsettling. A forecast model that has tracked every major El Niño event since the 1990s suddenly produced outputs that its own display system wasn't built to show. A chart, maintained by the National Oceanic and Atmospheric Administration, had to be physically redrawn. Not updated, not refined, redrawn. The y-axis, the vertical scale that marks temperature anomalies against the long-term average, had to be extended upward to plus 4 degrees Celsius because forecast members were running off the top of the previous range. Let that sit for a second. A model that has been running operationally for decades. A model that has seen 1997, that has seen 2015, that has processed every warm pulse and cold reversal the Pacific has thrown at it. That model, on a Friday morning in May, produced numbers it had never needed to display before, and the response from NOAA wasn't alarm. It wasn't a press release. It was quieter than that. They just extended the axis. They made room for what the model was showing, and they kept going. That is what we're going to spend the next hour talking about. Because here's the thing about that chart change. It might look like a technical footnote, a display issue maybe, a formatting quirk in a government data product that only a handful of atmospheric scientists and obsessive weather followers would even notice. But it is not a footnote. It is the opposite of a footnote. When a forecasting model that has been running without needing to change its output range for 30 plus years suddenly forces a redesign of its own display, the question you have to ask is, what did the data show that made that necessary? And more importantly, what are the agencies that operate these models seeing in the physics that they haven't yet said plainly in public? That tension between what the data is showing and what the institutions are willing to say out loud is the thing we're going to follow all the way through this video. Because it shows up everywhere once you start looking. It shows up in the difference between a chart axis and a press release. It shows up in the gap between a model ensemble and an official probability. It shows up in the distance between the word unprecedented and the sentence that word belongs in. And it starts on May 1st, 2026, with a forecast update that most people treated as routine. The model in question is the CFS v2, the Climate Forecast System, version 2. NOAA's primary seasonal prediction tool, the thing that has been cranking out ensemble members, essentially multiple runs of the same model with slightly different starting conditions, to produce what forecasters call a plume of possibilities. Under normal circumstances, you'd pull up that plume on any given week and see something that looks like a bundle of lines, spreading out as you move forward in time, showing the range of what the model thinks might happen to sea surface temperatures in the equatorial Pacific. The central cluster tells you the most likely outcome. The outliers tell you the edges of possibility, and the y-axis that holds all of this sits comfortably within a range that past experience has defined until May 1st. On May 1st, the plume didn't sit comfortably within anything. Ensemble members, individual model runs, were pushing above plus 3 degrees Celsius of anomaly. Not a few outliers, not one rogue run that you'd dismiss as a glitch. Multiple members were climbing toward ranges that the model's previous display scale had simply not included, and when enough members push high enough, you don't get to keep the old axis. You extend it, you make the chart taller, you move the ceiling up to plus 4 degrees Celsius, and you keep the model running, because the physics doesn't care about your display scale. Now, the number that keeps coming up when you look at where the ensemble is pointing is this, a December 2026 Oceanic Niño Index median of approximately plus 2.9 degrees Celsius. That's the ONI, the 3-month average sea surface temperature anomaly in the Niño 3.4 region of the Central Eastern Pacific, the number that forecasters use to define and measure El Niño events. Plus 2.9 degrees Celsius. And if that number doesn't immediately mean anything to you, let me give you some context that should sharpen it considerably. The 1997 to 98 El Niño, the event that, for decades, has been the definition of Super El Niño in public consciousness, the one that caused catastrophic flooding in California, destroyed fisheries along the South American coast, triggered droughts across Southeast Asia, and reshaped the global weather pattern for the better part of a year. That event peaked at approximately plus 2.4 degrees Celsius on the ONI. The 2015 to 16 El Niño, which tied or exceeded 1997 by some measures, and was broadly classified as one of the 3 strongest events in the modern instrumental record, peaked at approximately plus 2.6 degrees Celsius. Those 2 events are the yardsticks. They are the benchmarks. When scientists and forecasters talk about what a major El Niño looks like, they are usually pointing at one of those 2 events. The current median forecast for December 2026 is plus 2.9. That is not a marginal increase over what we've seen before. This is not a rounding error between one extraordinary event and a slightly more extraordinary one. There is a meaningful step, a physical step in terms of heat, in terms of Pacific Ocean energy, between plus 2.6 and plus 2.9 degrees Celsius of anomaly. And the model isn't showing plus 2.9 as its high-end outlier scenario. It is showing that as the median, the middle of the distribution, the central expectation around which the ensemble is clustering. And that is precisely the moment at which this stops being a story about a model doing something weird and starts being a story about something real in the physical climate system that has forced the model to do something weird. Because a model doesn't change its display range for no reason. A model doesn't produce ensemble members that run off the top of a 30-year-old chart without cause. Something in the ocean, in the atmosphere, in the current state of the coupled climate system, has put enough energy into this forecast that the instrument we used to measure it ran out of room. That's the signal, not the chart itself. What's behind the chart? So what is behind the chart? Part of the answer is what we can already measure, not what models are projecting, not probabilities assigned to scenarios, measured data in real time from real instruments sitting in and on the equatorial Pacific Ocean right now. And those measurements are, in some ways, more striking than anything the models are showing. Because measurements aren't hypothetical, measurements are what's already there. But we're going to come back to that in detail, because before we talk about what's in the ocean, we need to address a question that might already be forming in your head. If the CFS-V2 is showing something this extraordinary, are other models showing the same thing? Or is this one instrument behaving strangely while the rest of the modelling community disagrees? That question matters enormously, because one model behaving unusually can mean a lot of things, most of which don't require a redrawing of the chart's implications for the real world. But if multiple independent modelling systems from different agencies in different countries, using different numerical approaches and different data assimilation methods, are all converging on the same uncomfortable upper end, that changes everything. That takes you from something might be wrong with the model to something might be happening in the climate. So let's find out which one it is. Part 2. the quiet convergence. No one is headlining. Here is what would make this story easier to dismiss. If only one model were showing it. If the CFSV2 were out there on its own, producing its extended y-axis and its plus 2.9 degree median while every other modelling centre was shrugging and forecasting a moderate El Niño, you'd have a reasonable argument for scepticism. Models have warm biases. Models have cold biases. Models have systematic errors baked in from their parameterizations, their boundary conditions, their data assimilation schemes. A single model running hot while the rest of the ensemble disagrees is a known situation in operational forecasting, and the appropriate response is to wait toward the consensus and note the outlier. But that is not what's happening here. The European Centre for Medium-Range Weather Forecasts, the ECMWE, runs what many forecasters consider the world's most skillful seasonal prediction system. Their SEAS-5 ensemble, which like the CFSV2, runs multiple model iterations forward in time to produce a plume of possibilities, is telling a consistent story. Every member of the ECMWF ensemble is predicting El Niño development. Not most members, not a strong majority, every single one. And when you look at where that ensemble spread is reaching, you find something that mirrors what NOAA is showing. The upper end of the ECMWF plume is extending into plus 3 degree and above territory for the peak of the event. Then there's the Copernicus Climate Change Service ensemble, coordinated through the European framework of C3S. Same picture. Alignment with high-end outcomes. Forecast members clustering in ranges that correspond to what, in historical context, would be extreme territory. And then you have the institutional probability numbers, which are notable in a different way, because they are expressed differently, and the way they're expressed tells you something about the gap we keep circling back to. NOAA's Climate Prediction Centre puts the probability of El Niño emergence this spring at 61%. They put the probability of El Niño persistence through the Northern Hemisphere winter, that critical December to February window, at somewhere between 88 and 94%. The International Research Institute for Climate and Society at Columbia University, which runs an independent multi-model forecast, places the near-term development probability at roughly 70%. These are not cautious, hedged, maybe it happens numbers. These are forecasters who are essentially saying, this is coming. Now hold both of those things in your head at once. Institutional models saying El Niño at 88 to 94% probability through winter. Ensemble plumes reaching up into plus 3 degrees and beyond. ECMWF with every single member pointing the same direction. And yet, the officially stated probability of what they're calling a Super El Niño, defined roughly as an event exceeding the 1997 to 98 or 2015 to 16 peaks, is still being quoted at around 25% in some institutional summaries, 25% on an event that the model's central tendency is pointing squarely at. How do you reconcile those two things? The answer is in the shape of the probability distribution, and it's one of the more counterintuitive ideas in forecasting. So stay with me here, because it actually matters quite a lot. When a model ensemble produces a distribution of possible outcomes, what you typically report as the official probability of an extreme event is the fraction of ensemble members that fall above a specific threshold. If you define Super El Niño as exceeding plus 1.5 degrees on the ONI, and 60% of your ensemble members are doing that, you report 60% probability of Super El Niño. Simple enough. But here's where it gets interesting. Forecast distributions are not symmetric. They don't look like a perfect bell curve centered on the median with equal tails on either side. In complex nonlinear systems, and the coupled ocean-atmosphere system is one of the most complex nonlinear systems on Earth, the distribution can be skewed. The mean can sit in one place, while the tail extends further in one direction than the other. And what forecasters have noticed, and what several analysts have now pointed out explicitly, is that the upper tail of the current El Niño forecast distribution is extending further and faster than the lower tail. The models are not drifting symmetrically toward uncertainty. They are drifting asymmetrically toward the high end. And this creates a situation that the climate journalist Jeff Berardelli has articulated clearly, using the plus 2.9 degree median as an anchor point. When the central tendency of your forecast is already in record territory, the question of whether you assign 25% probability to Super El Niño depends heavily on exactly how you're defining super, because at plus 2.9 degrees of ONI anomaly, you are already in the territory of the two events that most people would call the strongest El Niños in the modern instrumental record. The label is trying to catch up to a distribution that has already moved. What this means in practical terms, and this is where we start circling back to the central question we opened with, is that the probability language hasn't caught up to what the physics is suggesting. The institutional numbers are real, they're calculated correctly by skilled scientists, and they represent genuine uncertainty about the magnitude of what's coming. Nobody is hiding anything or being dishonest, but the way probability is communicated can create an impression that the most extreme outcomes are unlikely, when what's actually happening is that the entire distribution has shifted upward, and the question of extreme is being redefined in real time. The probability hasn't caught up to the physics yet. That phrase is going to keep coming back, because we're seeing it not just in the ensemble spreads and the official probability statements, we're seeing it in the words that scientists themselves are choosing to describe what's happening. And those words, and the institutional logic behind them, deserve their own careful examination. Because the gap between what the data is saying and what people are willing to say about the data is not random. It has reasons, and those reasons are in some ways as important as the data itself. Part 3. The language gap. James Hansen says 2026 will be the warmest year ever recorded. He says it with the particular confidence of a scientist who's been making climate predictions for 40 years, watching them verify, and is now watching the system behave in ways that exceed even his own forecasts from a decade ago. Hansen's framing is declarative, assertive. He uses the language of high confidence projection. Zeke Hausfather, a climate scientist at Berkeley Earth, and one of the more careful quantitative voices in the field, frames the same situation differently. Probabilistic language, error bars, conditional statements. Not because he disagrees with Hansen on the underlying physics, he mostly doesn't, but because that's the epistemic standard he applies, the approach he thinks is most honest about what can and can't be known ahead of time. The Met Office, the United Kingdom's National Weather Service, calls the characterization of this event as unprecedented, premature. They're not dismissing the signal, they're applying institutional caution to a conclusion that, in their judgment, hasn't been established firmly enough to state in public with confidence. The World Meteorological Organization, the international body that coordinates global weather services, has allowed the word unprecedented into its language around this event, but carefully, provisionally, wrapped in hedging that acknowledges the WMO is not in the business of confirming records before they happen. 4 different voices, 4 different registers of certainty, all of them looking at essentially the same data. This is not disagreement in the way people usually mean it. These 4 framings are not pointing to different physical realities. The equatorial Pacific has one subsurface heat content, one set of Kelvin waves, one thermocline depth anomaly. The models are running on the same observations. What differs is the threshold at which each speaker feels comfortable translating a physical signal into a public statement. And that threshold is shaped by a set of institutional, professional, and historical considerations that have nothing to do with whether the physical signal is real. Let's talk about why scientific agencies communicate the way they do, because it's easy to misread their caution as uncertainty about the science when it's actually something more structural than that. Forecasting agencies live and die by their skill statistics. Every major climate and weather centre maintains historical records of its forecast accuracy, how often its predictions verified, how far off they were when they didn't, where systematic biases appear in the record, and those records create a real rational incentive for conservatism. A centre that calls a record-breaking El Niño 4 months in advance and then watches the event peak at merely strong but not record, has made a false positive call that will be cited in evaluations, in papers, in congressional testimony. A centre that calls it cautiously and the event turns out to be record-breaking is blamed much less, because the event itself becomes the news. The asymmetry of reputational risk pushes institutional language toward the centre, toward hedging, toward probabilistic framing that distributes credit for being right and distributes blame for being wrong. This is not cynical. It is rational. It is the accumulated professional wisdom of institutions that have been wrong before in high-profile ways, and have learned how to communicate under uncertainty in ways that preserve their credibility for the long run. But here's what that institutional logic doesn't account for. It was developed in a climate that looked like the past. The calibration of forecast conservatism, how cautious to be, how wide to set the uncertainty envelope, was built on decades of ENSO events that all existed within a certain range of the historical distribution. The language norms were calibrated against a set of possible outcomes that the physical system was then capable of producing. And the central argument we keep coming back to is that the physical system may now be capable of producing outcomes that are outside that historical distribution. Outcomes the language was never calibrated for. If you're a scientist who has spent your career carefully and accurately communicating about events that range from weak to very strong, and then one day the model shows something that your professional norms say requires more verification before you can state it publicly, you apply those norms. You're cautious. You wait. You say possibly unprecedented rather than unprecedented. You say premature rather than confirmed. That is what responsible scientific communication looks like, in a framework built for a climate that produced events within a familiar range. What it produces, when you apply it to a signal that may be outside that familiar range, is a gap between what the chart is saying and what the press release is saying, a gap between the y-axis extension and the official probability statement, a gap between what the instruments are measuring in the ocean right now and the language that's been chosen to describe it in public. The chart doesn't hedge. It can't. The model doesn't apply institutional risk calculus to its output. It takes in observations, runs the physics forward, and reports what the equations produce. And right now, what the equations are producing exceeds the range that 30 years of operational forecasting thought it needed to prepare for. The humans looking at those equations have every professional and institutional reason to be careful about what they say next. But those reasons, valid as they are, can create an impression of greater uncertainty about the physical outcome than the physical outcome actually warrants. And when we ask what are the agencies seeing that they're not willing to put in the press release, this is part of the answer. It's not that they're hiding something, it's that the norms of how they communicate were built for a climate that may no longer describe the one we're living in. And to understand why that might be true, why this event might be genuinely outside the range of what past experience can prepare us for, you have to go below the surface, literally. You have to go down into the water column, below the part of the ocean anyone can see from a satellite, to where the real story of this El Niño has been building since at least December of 2025. Part 4. The subsurface anomaly that changes everything. Forget the surface for a moment. When people talk about El Niño, they almost always talk about sea surface temperatures, the warmth you can see from space, the anomaly maps that show oranges and reds spreading across the central Pacific like a slow-motion fever. Surface temperatures are what define the ONI. They're what the media covers, they're what the graphics in the news show, and they matter enormously, but they're also, in a very real sense, the last thing to change. They're the symptom. What we really need to be looking at right now is the cause. As of April 2026, the equatorial Pacific Ocean is carrying the highest April subsurface heat content in the entire satellite era. Not the highest in recent years, not the highest since the last major El Niño. The highest April measurement ever recorded in the period for which we have comprehensive oceanic data, roughly since the 1980s when satellite coverage and the TO array of moored buoys came online. The Argo Float network, which has provided remarkable coverage of subsurface ocean conditions since the early 2000s, confirms it. The GODAS assimilation system, which synthesizes all of these observations into a coherent three-dimensional picture of the ocean's thermal state, shows it clearly. The numbers are extraordinary. At depths between 50 and 250 meters, the layer of the ocean that sits beneath the surface but above the permanent cold interior, temperature anomalies of +6 to +8 degrees Celsius have been recorded, not at one location, across a substantial portion of the central and eastern equatorial Pacific, and at around 300 meters depth, near a longitude of 110 degrees west. Anomalies approaching +7 degrees Celsius have been measured, 7 degrees warmer than the average for that depth at this time of year. Now you might be wondering, why does temperature at 300 meters depth matter for what happens at the surface? The surface is where weather happens. The surface is where you feel El Niño. So why are we down in the deep water? Think of it like a loaded spring. When you press down on a spring, you're storing mechanical energy in a compressed system. The surface of that spring doesn't look dramatically different from an uncompressed one, but the potential energy is there, Waiting. The equatorial Pacific thermocline, the layer where temperature drops rapidly with depth, separating the warm surface water from the cold deep, works in a similar way when it comes to ENSO dynamics. When anomalously warm water accumulates in the subsurface, it raises the thermocline depth anomaly. It loads the system with thermal potential energy. And that energy is not staying in the deep ocean. It is going to move. The timeline of this loading is important. Tracking the subsurface heat content record from December 2025 through April 2026, you don't see a sudden spike. You see a continuous increase. Month after month of measurements showing more heat in the subsurface column, a progressive loading of the spring, building toward a state that April's measurements have now confirmed as the highest on record for this calendar period. Compare this to 1997. In the months leading up to what became the dominant event of the late 20th century, the El Niño that became the benchmark for super, the subsurface heat content was substantial. The preconditioning was real. Scientists who were paying attention in early 1997 knew something significant was coming, even while the surface was still relatively calm. And the surface anomaly in early 97 was roughly comparable to where we are now, near neutral or slightly positive, not yet showing the dramatic warming that would develop through the summer and fall. But the subsurface in April 2026 is carrying more heat than April 1997 did. The surface right now sits at approximately plus 0.23 degrees Celsius of anomaly, near neutral. If you looked at only the surface, you'd say nothing unusual is happening. You might not even call it an El Niño watch. But the disconnect between a near-neutral surface and a record-loaded subsurface is not a contradiction. It's a timeline. It's the system telling you the heat is already there, below what you can see from space, and it is moving upward. Not immediately, not in a day or a week. But the physics of how the Pacific moves heat from the subsurface to the surface is well understood, and the direction is not in question. This is preconditioning at record levels. That phrase is worth sitting with, because it's easy to lose the physical weight of it in the abstraction of anomaly numbers. What it means in practice is that the raw thermal energy that El Niño draws on, the pool of heat in the equatorial Pacific that gets drawn to the surface by the changes in wind and ocean current that define the event, is, as of April 2026, larger than it has ever been at this time of year in the satellite record, before the event has even fully developed, before the surface has started to warm dramatically, before the models have anything close to verified. This is why the chart broke. This is why the NOAA plume had to have its y-axis extended to plus 4 degrees Celsius. Not because of a model glitch, not because of a parameterization error, not because of some numerical artifact in the CFS v2 system. Because the observational data feeding that model, the actual measured state of the equatorial Pacific Ocean right now, is at a level that makes plus 4 degree outcomes physically plausible in a way they never have been before in the operational history of the system. And if the subsurface is the loaded spring, then you need to understand the mechanism by which that spring gets released. You need to understand how the heat that's sitting at 300 meters depth right now makes its way to the surface in a way that shows up in an ONI reading of plus 2.9 degrees. Because that mechanism, those specific physical processes that carry heat from the depths to the surface, is itself producing signals that, right now, look unlike anything we've seen in the satellite era. Part 5. The Kelvin wave freight train. There's a physicist's term for a particular kind of wave that moves through the ocean along the equator. Not a surface wave, not the kind you'd body surf at the beach, but a subsurface disturbance that propagates eastward along the thermocline at several meters per second, carrying a pulse of warm water across the width of the Pacific Ocean. It's called a downwelling Kelvin wave, and what these waves do to El Niño is roughly what throwing gasoline on a fire does to the fire. They amplify it, they accelerate it, and once they've been generated, they can't easily be called back. The sequence of events that's building the current situation started in December of 2025 with what meteorologists call a westerly wind burst, a WWB. These are episodes of unusually strong westerly winds blowing from west to east, opposite to the trade winds that normally dominate the equatorial Pacific, that disturb the ocean's upper layer and generate Kelvin waves. The December burst generated a wave. That wave moved east along the thermocline. Then, in January 2026, another westerly wind burst occurred, another wave, moving east behind the first. The analyst Eric Webb, one of the more technically rigorous voices in ENSO monitoring, used the metaphor of a freight train to describe the effect, and it's a good one. Picture two freight trains, both moving at speed, both heading in the same direction. If the second one is close enough to the first, and the first slows down for any reason, the second runs into it and you don't get two separate trains anymore. You get an amplified collision, a combined impact that's greater than either would have produced alone. That's the stacking effect. And in the current configuration of the Pacific, multiple downwelling Kelvin waves have been propagating eastward in close enough succession that their effects are beginning to compound. Here's the mechanism, laid out plainly. In a normal year, the trade winds blow east to west. They push warm surface water toward the western Pacific, piling it up in what's called the warm pool near Indonesia and the Philippines. This piling up of warm water in the west depresses the thermocline in the west, pushes it deeper, keeps the warm water locked in. At the same time, it tilts the thermocline so that in the eastern Pacific near South America, the thermocline is relatively shallow. Cold water sits close to the surface. Marine ecosystems near the Peruvian coast thrive on the nutrients brought up by this upwelling of cold, rich water. When trade winds weaken, either from a natural variability in the atmospheric circulation or triggered by something like a westerly wind burst, the warm water in the west starts to slosh back eastward. The thermocline tilt relaxes. Kelvin waves carry the signal of this relaxation eastward along the thermocline, suppressing the shallow upwelling that normally keeps the eastern Pacific cold. The surface temperature in the east rises. The ONI ticks upward. That's the basic mechanism of El Niño onset. What's happening right now takes that mechanism and adds multiple layers. The Madden-Julian oscillation, the MJO, is a pattern of enhanced atmospheric convection that moves eastward around the tropics over the course of roughly 30 to 60 days, and it plays a significant role in generating westerly wind bursts. The MJO and WWBs interact with the existing oceanic state in ways that are notoriously difficult to predict far in advance, which is part of why seasonal El Niño forecasts always carry substantial uncertainty. But what the current pattern shows is a system that has been receiving repeated WWB forcing over a period of months, generating successive Kelvin waves, each one adding to the cumulative signal moving eastward through the thermocline. The stacking effect this produces is not just additive. In a system that's already carrying record subsurface heat content, each additional Kelvin wave that arrives in the eastern Pacific suppresses upwelling against a thermal background that's already warmer than anything in the modern record. The effect is multiplicative in a sense. Each successive wave of warm water transport arrives into an ocean that's already been preconditioned by the previous ones, and by the anomalous heat that was sitting in the subsurface before the first WWB even occurred. The system is not building momentum, it already has it. Now, this is where the uncertainty that forecasters are expressing actually does its most important work, because everything from here forward depends, to a meaningful degree, on what the winds do. The stacking of Kelvin waves requires continued westerly windburst activity. If the MJO enters a phase that suppresses WWBs for an extended period, the forcing slows down. The waves already in transit will still propagate and still warm the eastern Pacific. But the sustained forcing that could push the event from very strong to record-breaking is not guaranteed. It requires the atmosphere to keep doing what it's been doing, and the atmosphere, unlike the ocean, can change its configuration on timescales of weeks. This is the real source of the uncertainty you hear from forecasters, not uncertainty about whether El Niño is developing, which at this point is close to certain, but uncertainty about the magnitude, because the magnitude depends on continued atmospheric cooperation with a process that's already underway. The ocean's part is already committed, the heat is already in the system. What happens between now and December 2026 depends on whether the atmosphere keeps adding energy to a system that is already loaded to a level without modern precedent. And while we're on the subject of without modern precedent, there's another anomaly in the current situation that deserves attention, because it's the kind of thing that makes the physics scientists uncomfortable, in a way that's separate from the magnitude question. It's a question of timing, of how fast this has happened. Because the speed of the current development is itself something that the models weren't really built to expect. Part 6. The compression problem. Every El Niño event follows a broad developmental sequence. The ocean builds up a heat reservoir in the Western Pacific. This is called the recharge phase in what scientists term the ENSO recharge oscillator theory. Think of it like charging a battery. The warm pool accumulates in the west, the heat content builds, and eventually conditions become favourable for the reversal that we call El Niño onset. After the event peaks and dissipates, the system discharges. The Eastern Pacific cools, the Western Pacific takes time to rebuild its warm water reservoir. Then, eventually, you recharge again. The cycle has a characteristic timescale, roughly 3 to 7 years, that emerges from the physics of how long ocean heat content takes to build and deplete. The 2023 to 2024 El Niño followed this pattern more or less. It developed, peaked, strongly, though not at record levels, and then began to dissipate as 2024 progressed. Normal, if you treat ENSO as a system that operates on its own internal clock, cycling through recharge and discharge as it has done throughout the instrumental record. The anomaly in the current situation is how quickly the recharge appears to have occurred, or, to put it more precisely, how the system appears to have arrived at record subsurface heat content levels by April 2026, when, in theory, it should still be in the early stages of recharging from the previous event. The World Meteorological Organization has noted the rapid development of the current situation, adding its carefully placed qualifier of possibly unprecedented. And what makes it possibly unprecedented is in part this timing. Compare the developmental timeline. 2023 to 2024 ran roughly 14 months from onset to peak. The current development from the initial subsurface loading signal through the projected December 2026 peak is being compressed into something closer to 8 months. That is a fundamentally different timescale. That is a system that is not following the recharge oscillator's expected pacing. And the question, which scientists have not yet definitively answered, is why. One hypothesis is simply that the discharge from the previous event was incomplete, that the heat reservoir did not fully deplete when the 2023 to 2024 event wound down, leaving the system with a residual thermal charge that gave it a running start on the next cycle. A kind of double loading, where the recharge began from a floor that was already elevated rather than from a fully neutral state. If this is accurate, it means the ENSO system may be operating with a permanently raised floor, that what used to look like neutral conditions between events now looks like early-stage preconditioning, and the distinction between one El Niño ending and the next one beginning is getting blurry in a way it wasn't a generation ago. The other hypothesis, and this is where the physics gets genuinely speculative, though the speculation is grounded in real theoretical work, is that the background warming of the global ocean is changing the ENSO recharge oscillator's behaviour in ways that are not fully captured in the models. If the mean state of the Pacific is warmer than the historical average on which the recharge oscillator was calibrated, then the dynamics of how heat accumulates and discharges may be different. The timescales may be compressed, the amplitudes may be larger, the events may come faster and harder than the oscillator theory, derived from a cooler mean state, would predict. This is important to the central question we keep returning to, the question of why the chart broke, what the agencies are seeing that they're not saying plainly. Because if the ENSO system's fundamental behaviour is changing in ways that exceed the model calibration, then the model isn't showing you an outlier event within a distribution it understands. It's showing you an event that may have pushed outside the distribution it was built to simulate, and the language of institutional communication, which was calibrated for a world where the physical system operated within a known range, hasn't adapted to a world where the physical system may be operating outside that range. The system is accelerating faster than the models were calibrated for, and it's doing it on a planet that, in a very specific and quantifiable way, is not the same planet that any previous El Niño has ever operated on. Part 7. The Background State Shift. Every El Niño that has ever been recorded, from the earliest instrumental measurements through the great events of the 20th century, happened in a particular planetary context. The mean global surface temperature was lower, the ocean heat content was lower, the atmospheric concentration of greenhouse gases was lower. These are not background conditions that are separate from ENSO. They are the substrate on which ENSO operates, and they have changed. The global mean surface temperature in 2026 is roughly 1.4 to 1.5 degrees Celsius above the pre-industrial baseline, depending on whose dataset you use and how you define pre-industrial. That is an enormous shift in the planetary energy budget. Every degree of mean warming represents an additional flux of heat through the climate system, changing the baseline against which all anomalies are measured. When you say the Niño 3.4 region has a sea surface temperature anomaly of plus 2.9 degrees, that plus 2.9 is measured against a historical average that itself has been rising. The absolute temperature of the eastern equatorial Pacific is higher than it was when the 1997 event set its records, and it's higher again than when the 2015 event set its records. This matters for El Niño in a way that's easy to understate. And El Niño doesn't just add its anomaly on top of a fixed baseline, it adds it on top of whatever the current mean state of the ocean and atmosphere happens to be. And the current mean state is warmer than at any point in the history of El Niño measurement. So when an El Niño of a given ONI magnitude occurs in 2026, the absolute impacts, the surface temperatures in affected regions, the rainfall anomalies, the stress on ecosystems that have already been warmed, are greater than those of an El Niño with the same ONI value in 1997. Same mechanism, different starting point, same ENSO physics, different planet. There's a specific factor in the current background warming that's worth examining, because it's often overlooked in discussions of recent temperature anomalies, and it contributes to understanding why the current situation may be more extreme than the models initially expected. In 2020, the International Maritime Organization implemented a regulation called the IMO 2020 sulfur cap. It sharply limited the sulfur content in shipping fuel globally. The result was a rapid and substantial reduction in sulfur dioxide emissions from the world's cargo shipping fleet, a fleet that, prior to the regulation, was effectively operating as an inadvertent geoengineering system by emitting enough sulfur to create reflective aerosol hazes over the major shipping lanes. Those aerosol hazes reflected incoming solar radiation. They contributed a small but measurable cooling effect on the ocean surface temperatures in their vicinity. And when the IMO 2020 regulation removed them, that inadvertent cooling went away. Climate scientists have estimated the contribution of the shipping aerosol reduction to global surface warming at roughly plus 0.046 degrees Celsius this decade. Not enormous in isolation, but in a system where every fraction of a degree matters, where the difference between an El Niño reading of plus 2.4 and plus 2.9 is the difference between a historical benchmark event and something beyond it. A background warming contribution of nearly 0.05 degrees is not nothing. The IMO 2020 effect didn't cause the current El Niño. It isn't driving the Kelvin waves or the WWBs or the subsurface heat anomaly. But it contributed to raising the floor against which all of this is playing out. And raising that floor means that the same El Niño mechanisms that produced the results they did in 97 and 2015 are now operating at a higher absolute temperature, with more background energy in the system, in an ocean that was already warmer before the first westerly wind burst of 2025 even occurred. Post-2020, the transitions between ENSO states have appeared smoother, the neutral periods between events less neutral, and the events themselves potentially more extreme. This isn't a proven causal chain yet. Attribution in a complex climate system is hard, and the scientific papers making these connections are still working through peer review and debate. But the observational record since 2020 is consistent with the hypothesis that something about the background state has shifted in a way that changes how ENSO events develop and peak. So put all of this together: record subsurface heat content, compressing development timescale, multiple stacked Kelvin waves, and a background mean state that's higher than any previous El Niño in the instrumental record has ever operated against. All of that is what the CFSV2 was ingesting when it produced an ensemble that ran off the top of its own chart. All of that is what's behind the y-axis extension. And all of that is what makes the question of how extreme this event might actually get a genuinely difficult one. Not because the science is unclear, but because the physics may now be producing something that the historical record doesn't fully constrain. Which brings us to the question we've been building toward. Not whether an extreme event is coming, not whether the models agree, not whether the institutions are communicating it adequately. The question of what extreme actually means in the context of this specific event, on this specific planet, in this specific moment. And to answer that, you have to look at the most extreme comparison that climate science has available, the one that sits at the outer edge of what El Niño has ever been documented to produce. Part 8. The 1877 Comparison. There is an event in climate history that sits at the edge of the record, not at the edge of the satellite era, not at the edge of the 20th century instrumental period, but at the edge of what can be reconstructed from historical ship logs, coral proxy records, and colonial administrative documents that survived the decades. It is the El Niño of 1877 to 1878, and if you haven't heard of it, that is partly because the history of that event is inseparable from the history of what it did to the people who lived through it, and that history is not something that gets discussed as casually as a weather record. The Great Drought, as it came to be known across the affected regions, was a consequence of the 1877 to 78 El Niño triggering monsoon failure across South Asia, Brazil, China, and parts of sub-Saharan Africa, essentially simultaneously. The disruption to rainfall patterns across 3 continents, occurring in a period of colonial governance that prioritised export production over food security and relief, was systematically denied or delayed, contributed to what historians of climate and colonialism estimate at somewhere between 30 and 60 million deaths. That is not a footnote. That is one of the deadliest climate-related events in human history, and it was driven by an El Niño event whose magnitude we are still trying to accurately reconstruct. That reconstruction uncertainty is important. The conventional estimate for the 1877 to 78 ONI equivalent is approximately plus 2.7 degrees Celsius, which, if accurate, would place it roughly at the level of the 2015 to 16 event. But more recent paleoclimate reconstructions using coral records from the Pacific produce a wider range, with some estimates extending up to plus 3 degrees or somewhat higher. The honest scientific answer is that we don't know the exact magnitude of the 1877 to 78 event. The proxy records available for the pre-instrumental period don't have the precision that modern thermometers and buoy arrays provide. What we do know is that the effects were at a level that exceeded any documented El Niño in the modern instrumental record. Monsoon failures of that severity, affecting that many regions simultaneously, require an exceptional thermal forcing from the Pacific, and the current forecast median of plus 2.9 degrees, which sits above the conventional reconstruction of plus 2.7 and within the upper range of the uncertainty envelope on the proxy reconstructions, means that we are now within reach of the strongest known event in recorded climate history. We're not saying the 2 events are equivalent. We're not saying the impacts would be the same. The world of 2026 is profoundly different from 1877 in terms of global food systems, communication, water infrastructure, and the capacity to respond to climate disasters. We're also not dismissing the magnitude comparison, because the physical forcing is what matters for understanding what the atmosphere and ocean will do, regardless of how human systems respond. What the comparison tells us is this: the current forecast puts the projected peak of this event in the same neighbourhood as the strongest El Niño that human civilization has documented evidence of experiencing. That alone should clarify why the chart broke. That alone should clarify why the language is hedged the way it is. The agencies saying premature and possibly unprecedented are not being evasive. They are grappling with the fact that the comparison they are being asked to make requires them to say something about the current situation that has no modern analogue, something that was not in the probability distribution they were operating against when they calibrated their communication norms. Now, here is where we need to talk honestly about what might go wrong with this forecast. Because the most extreme projection is not the certain one, and understanding why it might not verify is just as important as understanding why it might. Part 9. Why this might not verify. The May forecast. There is a reason that forecasters have a name for this particular time of year in the context of ENSO prediction, the spring predictability barrier. It is a well-documented, well-understood, genuinely frustrating feature of how El Niño forecasting works, and it means that predictions made in the April to June window have systematically lower skill than predictions made in later months. The reason is rooted in ocean-atmosphere coupling dynamics. During the Northern Hemisphere spring, the equatorial Pacific tends to be in a state where its sensitivity to atmospheric forcing is lower. The signal-to-noise ratio in the observational data is reduced, and small errors in the initial conditions of a model can lead to large divergences in the forecast outcome. It's not that forecasters know less in May. They have as many observations, as much satellite coverage, as many buoy readings as at any other time of year. It's that the ocean's response to the atmospheric forcing it receives during this window is inherently less predictable. The coupling is weaker, the signal is harder to read. This means that May forecasts for December, even when driven by record subsurface heat content and strong model consensus, carry more uncertainty than the raw ensemble spread might suggest. The ensemble spread itself is one measure of model uncertainty. But the spring predictability barrier adds structural uncertainty that the spread alone doesn't fully capture. Then there's the warm bias issue. The CFSV2, the NOAA model that produced the y-axis extension we opened with, has a documented tendency to run warm in its ENSO forecasts. This bias has been characterized at roughly plus 0.2 to plus 0.5 degrees Celsius in ONI forecasts. That's not a trivial number when your central forecast is plus 2.9. Apply a conservative bias correction of plus 0.3 degrees and you bring the corrected central estimate to roughly plus 2.6, which still corresponds to one of the 2 or 3 strongest events in the modern instrumental record. The important point, and this is the key insight that survives even the most aggressive application of bias correction and spring predictability uncertainty, is that the conservative case is still an extreme event. If you correct for every systematic warm bias, apply appropriate inflation to the uncertainty envelope, and hold the spring predictability barrier in mind, you still end up with a central estimate that sits at the top of the modern record or very near it. The question is not whether this will be a major El Niño. The models agree on that at 88 to 94% probability. The question is how major turns out to be. And critically, this is where the distribution shape matters more than the mean. The downside scenario and the upside scenario are not symmetric. The spring predictability barrier and the warm bias work together to suggest that the forecast might be too high. But the record subsurface heat content, the stacking of Kelvin waves, the compressed development timeline, and the elevated background state all work in the direction of suggesting the forecast might actually be too low. There are specific physical reasons why this event might exceed expectations, just as there are specific statistical reasons why it might fall short of them, and those physical reasons deserve to be taken as seriously as the statistical ones. Part 10. Why it might exceed expectations. The cases for upside surprise in ENSO forecasting are usually subtle. Small changes in wind forcing, slightly stronger coupling between the ocean and atmosphere, marginal differences in the initial state. This time, the case for upside surprise is built on factors that are neither small nor subtle. The background sea surface temperature in the tropical Pacific basin, not just the anomaly, but the absolute temperature, is higher than at any comparable point in the modern record. This matters because the atmosphere's response to a given sea surface temperature anomaly is not linear. Atmospheric convection, the thunderstorm activity that drives the large-scale weather patterns ENSO modifies, is particularly sensitive to absolute sea surface temperature rather than just anomaly. At higher absolute temperatures, the atmosphere responds more strongly to the same degree of warming anomaly. The same ONI value in 2026 will drive more atmospheric response than the same ONI value in 1997, because the absolute temperature it's building on is higher, and the atmosphere's sensitivity scales with that. This is the mechanism through which background warming can amplify ENSO impacts non-linearly. It's not just that the floor is higher, it's that the amplifier gain has increased. The same physical forcing from the Pacific produces a stronger atmospheric circulation response, which feeds back into the ocean coupling, which can then amplify the ENSO signal further. This non-linear feedback is precisely what standard model calibrations built on historical data from a cooler mean state might be underestimating. Then there's the question of regime shift. This is speculative language. Climate scientists use it carefully because regime shifts are easier to identify after the fact than in real time. But the observational record of the past several years is consistent with the hypothesis that the Pacific has undergone some kind of shift in its mean state. The post-2020 period has been characterized by persistently elevated global temperatures, a series of ENSO events that have developed more rapidly than historical precedent would predict, and a background oceanic heat content that has not returned to pre-2015 levels between events. If this is a regime shift, if the Pacific has moved into a new state in which the ENSO cycle operates at a higher baseline and produces more extreme events, then the current forecast may be the first data point in a new distribution rather than an extreme outlier in the old one. The broader climate sensitivity debate is relevant here too. There is ongoing scientific discussion about whether the Earth's climate sensitivity, its equilibrium response to a doubling of atmospheric carbon dioxide, is at the higher end of the estimated range or the lower end. If climate sensitivity is higher than the central estimate that most climate models use, then the amount of warming that has occurred from the observed greenhouse gas forcing is greater than expected, and the background state elevation we're seeing is consistent with a high-sensitivity world. In a high-sensitivity world, ENSO events are riding on a warmer mean state than even the current generation of climate models is fully capturing. The phrase that captures this possibility, and it's a phrase that should stay with you, is this. This event may not be an outlier. It may be a preview, not a preview of the next Super El Niño, which may come in 5 or 7 years. A preview of what El Niño looks like from here forward. A first glimpse of what the distribution of ENSO events looks like in a climate that has moved into a new regime. If that's true, then the chart that NOAA had to extend on May 1st, 2026 wasn't extended because something unusual happened. It was extended because the old chart was no longer adequate for the world we're now living in, and we just didn't know it until the model told us. Part 11. The temperature. Question. James Hansen says 2026 will be the warmest year on record. Let's sit with that claim for a moment, not to adjudicate it, but to understand what it's built on, and why even the scientists who agree with the underlying physics frame it differently. El Niño events and global temperature records have a complicated relationship. It's not that El Niño directly raises global temperatures in the way that greenhouse gas forcing does. The mechanism is different. What El Niño does is shift heat from the ocean interior to the surface and atmosphere, releasing stored thermal energy in a way that shows up in global temperature averages. This is why the warmest years in the modern instrumental record have often followed El Niño peaks. 1998 was the warmest year on record when it happened, following the peak of the 1997-98 event. 2016 was the warmest year on record when it happened, following the 2015-16 event. The pattern is consistent. The lag is important. The global temperature response to an ENSO peak typically follows the peak by roughly 6 to 12 months. This means that if the current El Niño peaks around December 2026, as the model median suggests, the maximum global temperature impact might not appear until mid to late 2027. Hansen's forecast of 2026 as the warmest year may be correct if the ENSO peak comes earlier than the median forecast, or if the surface warming develops faster than historical analogues suggest. Alternatively, if the peak is closer to December 2026, the warmest year on the record books might be 2027. But the timing debate, 2026 or 2027, somewhat obscures the more fundamental point, which is where this connects back to the central thread we've been following. Whether it's 2026 or 2027, the global temperature record will be set during or after an El Niño event that the models are projecting at a level beyond anything in the modern instrumental record, on a background baseline that is already the highest in measured history. The institutions saying premature to call the full magnitude of this event are correct in a technical sense. The institutions saying 2026 or 2027 will be record warm years are almost certainly correct in a predictive sense. The language gap between those two positions is precisely the gap we opened this video with, the chart saying something that the press releases haven't fully caught up to yet. The 2024 baseline complicates the record-setting question in an interesting way, because 2024 itself was a record warm year, established on the declining tail of the previous El Niño and the elevated background state. The 2027 peak will need to exceed a higher bar than 2016 had to clear over 2015. This is what a climate that's warming looks like in the statistics. Consecutive records become harder to set because each new record raises the standard for the next one. But the physical forcing available from the current event, if it verifies at or near the forecast median, is substantially larger than what drove the 2024 record. Part 12. Carbon Cycle Acceleration. While we're talking about what this event might do to global systems, there's a feedback loop that doesn't get nearly enough attention, one that connects El Niño events to the very atmospheric greenhouse gas concentration that's amplifying them. It runs through the global carbon cycle, and when it activates, it turns a weather event into something with implications for the pace of climate change itself. The 2015-16 El Niño produced a measurable spike in the annual growth rate of atmospheric carbon dioxide. The mechanism runs through the tropics, When El Niño brings drought to normally wet tropical regions, Indonesia, the Amazon basin, parts of Central Africa, the vegetation that normally absorbs substantial quantities of carbon dioxide from the atmosphere comes under stress. Photosynthesis slows, soils dry out and in some cases begin to emit CO2 from decomposing organic matter. And in the case of the 2015-16 event, fire contributed substantially. The Indonesian peat fires of 2015 alone released an extraordinary amount of stored carbon that had accumulated over centuries. Then there was 2023. The Amazon basin, normally a carbon sink of global significance, one of the largest on Earth, reversed its behaviour. Instead of absorbing carbon dioxide, the stressed, drought-affected, in some areas burned Amazon forest began emitting it. A sink became a source. The contribution to atmospheric CO2 from a temporarily reversed Amazon sink is not negligible at the scale of the global carbon budget. An El Niño event peaking at or above plus 2.9 degrees ONE would drive drought over the tropics at a level that the 2015-16 event, peaking at plus 2.6, already showed produces carbon cycle disruption. The feedback loop is not hypothetical. It has already been observed twice in the satellite era. The question for the current event is whether a stronger peak, on a background of already stressed tropical ecosystems that have been dealing with elevated temperatures and drought stress continuously for the better part of a decade, produces a proportionally larger carbon cycle response, or a non-linearly larger one. This is the compression problem from the physical oceanography section now appearing in the biogeochemistry. If the ENSO cycle is compressing, if events are coming faster and stronger, and if each event stresses the same tropical ecosystems before they've fully recovered from the last one, the carbon cycle feedback may not scale linearly with event magnitude. It may cascade. And that means this El Niño's legacy, measured in atmospheric CO2 growth rate, might extend well beyond the peak of the event itself, feeding back into the very background warming that helped create it in the first place. This is what makes the language gap matter beyond the immediate forecast. What the data is showing isn't just about temperatures and rainfall anomalies, it's about the pace of the feedback loops that will define what comes after. Part 13. Weather redistribution. The redistribution of rainfall that El Niño produces is not subtle, and it is not equal. India's monsoon, upon which roughly 1 billion people depend for agricultural water supply, shows sensitivity to ENSO state that historical records make clear. An El Niño year in India is, in the statistical expectation, a below-average monsoon year. Current seasonal forecasts for the Indian monsoon are citing El Niño-related risk factors and placing the rainfall probability near roughly 92% of the long-period average, which sounds close to normal, but represents a meaningful deficit across a country that already pushes the boundaries of its water resources. Indonesia and northern Australia face drought signals that correlate with the Pacific warming in the central and eastern basin. Early 2026 already showed fire-related signals in Patagonia, consistent with the kind of circulation anomalies that accompany developing Pacific warmth. And on the other side of the ledger, because El Niño's redistribution has winners as well as losers in the rainfall budget, South America's western coast and portions of the southern United States tend toward anomalously wet conditions during strong events, bringing flood risks to landscapes that are sometimes drought-affected in La Niña years. These are the teleconnections, the statistical fingerprints of ENSO in weather patterns far from the Pacific, transmitted through the global circulation of the atmosphere. The mechanism is real, the signal is repeatable, and the magnitude of these remote impacts scales with the magnitude of the Pacific event. The fact that the models are projecting an event at or near the top of the modern record is not just a story about the Pacific. It's a story about every region whose climate is linked, through those teleconnections, to what happens in the equatorial Pacific Ocean over the next 12 months. The chart that broke on May 1st isn't just a Pacific story, it's a planetary one. Part 14. The Hurricane Paradox. There is a counterintuitive consequence of El Niño for Atlantic hurricane activity that creates what looks, on the surface, like a contradiction in the current forecast picture, and it's worth a brief examination because it illustrates the complexity that keeps institutional language cautious even when the primary signal seems clear. El Niño events produce increased vertical wind shear over the tropical Atlantic. That is, stronger differences in wind speed and direction at different altitudes. Wind shear is the principal enemy of hurricane formation and intensification. Hurricanes are organised columns of rotating convection that require relatively uniform wind flow through the depth of the troposphere to maintain their structure. When wind shear increases, it tears at the tops of developing storms and disrupts the organisation required to sustain them. The result, historically, is that strong El Niño years tend to produce below-average Atlantic hurricane seasons. The Colorado State University Forecast Group, one of the most respected seasonal hurricane forecasting operations in the world, released projections for the 2026 Atlantic season that are consistent with this El Niño suppression effect, a forecast for below-average activity compared to the recent highly active seasons. But here's the paradox. The Atlantic's sea surface temperatures, the raw fuel for hurricane development and intensification, separate from the wind shear question, remain substantially elevated relative to historical norms. The background warming that amplifies the El Niño signal is not confined to the Pacific. It's planetary. And warm Atlantic waters, all else equal, favour hurricane intensification. The current situation puts the primary suppression mechanism, wind shear from El Niño, in direct competition with the primary fuel mechanism, warm Atlantic SSTs, in a way that makes the forecast more uncertain than a standard El Niño equals quiet hurricane season relationship would suggest. This paradox is exactly the kind of thing that keeps scientists careful about sweeping statements. Because the overall El Niño magnitude story says one thing about Atlantic hurricane risk, and the absolute temperature story says something slightly different, and resolving the two requires the kind of nuanced probabilistic thinking that doesn't fit neatly into a headline. The chart that broke on May 1st tells you something definitive about the Pacific. It tells you something more complex and conditional about every downstream consequence, which is precisely why the language gap exists, and precisely why understanding the gap matters more than trying to close it prematurely. Part 15. When models outrun their design. Let's return to the chart. We started there, on May 1st, 2026. The CFS-V2 forecast plume, the y-axis extension to +4 degrees Celsius, the ensemble members running off the top of the previous range. We've spent the last hour building a physical case for why that happened. The subsurface heat, the Kelvin waves, the compressed timeline, the elevated background state. Now it's worth asking what it actually means for a model to exceed its own designed range, and what that tells us about the state of the science. The CFS-V2 is a remarkable piece of scientific infrastructure. It incorporates decades of development, assimilation of enormous volumes of observational data, parameterization schemes that have been refined through continuous comparison with real-world outcomes. It is, in many respects, a monument to what applied atmospheric and ocean science can achieve, and it was designed with a certain range of expected outputs in mind, a range that was calibrated against the historical record of ENSO events, the strongest of which reached approximately +2.5 to 2.6 degrees on the ONI. When the model produces ensemble members that exceed +3 degrees and push toward +4, it is not failing. The equations are running correctly. The physics it was built to simulate is being simulated. What has happened is that the physical reality being fed into those equations, the actual state of the equatorial Pacific Ocean in 2026, has produced outputs that are beyond the range the model's designers needed to display. They didn't include a y-axis that went to +4 degrees, because historically they never needed one. It's like a thermometer that was built for a laboratory that never gets above 120 degrees Fahrenheit, suddenly being operated in an industrial setting where temperatures hit 150. The thermometer isn't broken. The thermometer was just never designed for this environment. This is a conceptually important distinction. When the chart broke, it wasn't because the model failed. It was because the model succeeded in simulating a physical state that exceeds what the historical record led its designers to prepare for. The model didn't produce an error. It produced a result that the infrastructure around it wasn't expecting. And that infrastructure, the display systems, the communication frameworks, the probability tables, the institutional language, is all now scrambling to adapt to data that the physical climate system has produced without asking permission. There's a broader principle at work here that's worth naming explicitly. Climate models, like all scientific instruments, have a calibrated range of validity. They are built and tested against observational data. Their parameters are set to reproduce the historical climate record. And when the physical system moves beyond the range that the historical record covers, the models enter what you might call extrapolation territory. They're running physics equations that are still valid, but applying them to initial conditions and boundary conditions that fall outside the range of states used to validate and calibrate them. That doesn't make the outputs wrong, but it does mean that the uncertainty around those outputs should be wider than the model's internal statistics suggest, because the model's internal uncertainty estimates were themselves derived from a calibration set that didn't include states like the current one. The chart broke because the physical climate system produced something the model's designers hadn't needed to prepare for. The question we should be asking is not, when will the chart be fixed, but what else in our climate infrastructure wasn't designed for the world we're now living in? Part 16. The Hidden Constraint. Scientific Language. Let's be precise about something, because this is the part where it's easy to go wrong. The gap between what that chart is showing and what the press releases are saying is real. It has causes. It matters. But it does not mean that scientists are lying to you. It does not mean that NOAA, the ECMF, the Met Office, or the World Meteorological Organization are looking at the data, understanding the full implications and choosing to hide them from the public. That framing is wrong, it is unfair, and frankly it misses the far more interesting truth about what is actually happening here. What is actually happening is more structural than that, and in some ways more unsettling. The researchers and forecasters running these systems are applying genuinely important epistemic standards, the kind of rigorous evidence-based caution that makes scientific communication trustworthy over the long run. The lag between what the observations are showing and what gets stated publicly is not a cover-up. It is a feature. It is how the system is supposed to work. The problem is that the system was designed for a different climate than the one currently loading heat into the equatorial Pacific at record levels. Think about how scientific communication norms actually develop. They don't emerge from nowhere. They are built through decades of experience, forecasts that verified, forecasts that failed, high-confidence calls that embarrassed institutions publicly, cautious calls that turned out to be exactly right. Every norm about how to phrase a probability statement, when to use the word unprecedented, how wide to set an uncertainty envelope, all of it was calibrated against a historical record of ENSO events that fell within a certain range, a range defined by what the physical climate system had actually produced in the period during which humans were carefully measuring it. And here is the core issue. Those norms do not automatically update themselves when the physical system moves beyond that range. They update slowly, through peer review, through the accumulation of evidence across multiple events, through the gradual, careful revision of institutional positions as the data becomes so overwhelming that the old language simply cannot contain it anymore. That process is legitimate. It is how science maintains its credibility. But it takes time, and in the meantime, between the moment the data crosses a threshold and the moment the institutional language catches up to that threshold, there is a gap, a real one, with real consequences. Now consider the specific history that has shaped how El Niño agencies communicate today, because it explains a great deal about the caution you're currently seeing. The 1997-98 El Niño is celebrated now as a forecasting triumph, the event that proved seasonal prediction was possible, that demonstrated the value of the TAO buoy array and the modelling infrastructure that had been built through the 1980s. But that triumphant narrative is somewhat reconstructed after the fact. In the early stages of that event, several major modelling centres initially characterised it as a moderate El Niño. The data forced revisions upward over subsequent months. The final magnitude exceeded what the early forecasts had confidently stated. The triumph was real, but it was messier in real time than the retrospective tells. Then there was 1994 to 95. That event was, at one point in its development, forecast by multiple centres as a potential super El Niño. It had characteristics in the early data that looked, in some respects, like a system building towards something extraordinary. It peaked as a moderate event. The gap between the high-end forecast and the verified outcome was substantial, and it was public, and it was remembered. Institutionally remembered. The kind of memory that gets baked into communication guidelines, into the thresholds for using certain language, into the internal culture of forecast agencies where people who were there in '94 still work. These experiences are not paranoia. They are rational risk management by organisations that operate in public, that are accountable to governments and taxpayers, and that have learned through hard experience what the cost of a high-profile false positive looks like. That caution is earned. It deserves respect. And it is precisely why the current situation is so uncomfortable. Because the caution that is rational and appropriate based on institutional history is now being applied to a physical signal that may be categorically different from the signals that generated that history. Here is the asymmetry that makes the current moment genuinely difficult, and I want you to sit with this because it does not resolve neatly. When an agency is cautious about calling a super El Niño and the event turns out to be moderate, the outcome is that the agency was appropriately careful. Their forecast communicated genuine uncertainty. They were correct about the limits of what could be known. The cost of that caution is essentially zero. Perhaps some scientists feel privately that the hedging was excessive, but no one suffers because a cautious forecast preceded a moderate event. Now run the scenario in the other direction. An agency is cautious about calling a potentially record-breaking event. They apply their standard institutional language, they cite uncertainty, they note the spring predictability barrier, they assign a 25% probability to the most extreme outcome even though the model median is already sitting in record territory. And then the event breaks records, then the monsoon fails, then the drought begins, then the governments and aid organisations and water utilities and farming communities that were making preparation decisions in the months before peak, decisions that required information about the plausible range of outcomes, find out that the information available in the data was more extreme than the language used to communicate it suggested. The scientists were not wrong technically, the uncertainty was real, the caution was professionally defensible, but the practical consequence, whether the people and institutions that needed to prepare had adequate information to do so, is a different question from whether the forecast communication followed correct epistemic procedure. And those two questions have different answers. Language is lagging behind data. That is the situation we are in right now, on this specific event, in this specific May of 2026. The chart that had to be extended on May 1st showed something that will require, if it verifies at or near the current median, a fundamental revision of the language used to describe extreme ENSO events. The word unprecedented will need to move from a hedge to a statement of fact. The probability tables will need to be recalibrated against a distribution that has shifted upward. The institutional communication frameworks will need to be rebuilt around a new upper bound that the old framework simply did not include. But that revision, by the nature of how scientific institutions work, will not be complete until after the event has accumulated enough verified data to make the revision undeniable. The process requires that. The credibility of the process requires that. You cannot revise the language ahead of the evidence, because the moment you do, you have undermined the very epistemic standard that makes the language meaningful. And so, the physical climate system and the institutional communication framework find themselves in a race that the climate system did not agree to run slowly. The ocean does not wait for peer review. The subsurface heat content does not hold at record levels, while the agencies update their thresholds. The Kelvin waves do not pause propagation, while the probability tables get recalibrated. This is not a criticism of the scientists, not even slightly. It is an observation about the structure of a situation that nobody designed and nobody chose. A situation in which the pace of physical change in the climate system has outrun the pace at which the institutions built to monitor and communicate about that system were designed to adapt. Not because the institutions are slow, not because the scientists are negligent, but because the climate is moving faster than the framework built to track it was ever calibrated to expect. The chart on May 1st didn't just need a new y-axis, it needed a new framework. And the distance between those two things, between extending a display scale and rebuilding the conceptual infrastructure of how we talk about what the climate is now capable of producing, is exactly the distance that separates what the data is showing from what the press release is saying. And that distance, right now, is not small. Part 17. The real uncertainty. There is a distinction that gets lost almost every time El Niño enters public conversation, and right now, in this specific forecast cycle, that distinction matters more than it ever has before, because the way you frame uncertainty determines what you do about it. And the current framing, the one showing up in most headlines, most official probability statements, most public summaries of where this event is heading, is, without being technically wrong, telling you the least useful version of the truth. So let's separate two questions that keep getting collapsed into one. Because they are not the same question, they do not carry the same uncertainty, and conflating them is causing people to dramatically underestimate what the current data is actually communicating. The first question is whether an extreme El Niño is developing. And the honest answer to that question, as of May 2026, is that it is close to settled. The NOAA Climate Prediction Center places the probability of El Niño persistence through the Northern Hemisphere winter, that critical December through February window when the event would reach its peak, at between 88 and 94%. Every single member of the ECMWF ensemble, the European modelling system that many forecasters consider the most skillful seasonal prediction tool on the planet, is pointing in the same direction. Not most members, every one. The subsurface heat content in the equatorial Pacific is at the highest April level ever recorded in the satellite era, and there is no physical mechanism by which that heat disappears before it reaches the surface. It will upwell. The thermodynamics are not negotiable. The uncertainty about occurrence is real. 90% probability is not certainty. But in the context of seasonal climate forecasting, where the spring predictability barrier makes confident long-range calls genuinely difficult, an 88 to 94% probability of persistence is about as close to settled as this science gets. If you're making decisions that depend on whether a significant El Niño event occurs this year, the answer the data is giving you is plan for it. The residual uncertainty is not large enough to justify treating the event as a coin flip. The second question is entirely different. The second question is how big this gets, and that question, the magnitude question, is where the genuine, significant, scientifically honest uncertainty lives. How far above +2 degrees will the Oceanic Niño Index peak? Will the spring predictability barrier inject enough noise into the forecast to pull the verified outcome meaningfully below the current model median? Will the atmospheric forcing, the westerly wind bursts, the Madden-Julian oscillation activity, the sustained low-level wind patterns that have been stacking Kelvin waves in the subsurface, continue through the summer in a way that maintains the momentum the system has already built? These are real unknowns. They have real physical bases, and they determine the difference between an event that is extraordinary by historical standards and an event that is without modern precedent. That distinction, occurrence versus magnitude, is the one that gets lost, and losing it produces a specific kind of miscommunication that has practical consequences. When you read that the probability of a super El Niño is 25%, your brain registers a low probability event. 1 in 4, not likely. May be worth keeping an eye on, but not the thing you reorganize your planning assumptions around. That framing is technically consistent with the underlying model data. The 25% number, calculated correctly from the ensemble distribution against a specific threshold definition, is a legitimate statistical statement. But here is what that same underlying model data is also telling you, in a framing that the probability statement does not capture. Even under conservative assumptions, this event's floor is in record territory. Think about what that means. Apply the CFSS-V2 warm bias correction. Reduce the forecast by the documented +0.2 to +0.5 degree systematic overestimation the model is known to carry. Inflate the uncertainty envelope for the spring predictability barrier, giving the forecast extra room to be wrong in the downward direction. Assume a scenario where the atmospheric forcing becomes less favourable over the summer, where the MJO shifts to a phase that suppresses further westerly wind burst activity, where the Kelvin wave stacking weakens from here. Run all of those conservative adjustments simultaneously. What you get is still an event that belongs in the top tier of every El Niño in the modern instrumental record. The downside scenario of the current forecast, the outcome you'd get if most things go less favourably than the median projects, is itself extreme by any standard that the history of ENSO measurement has established. That is not a low probability event wearing a 25% label. That is a situation where the floor has been raised to a level that, in any previous forecast cycle, would have been considered the high-end tail scenario. The distribution has shifted, the entire range of plausible outcomes has moved upward, and the probability language, anchored to fixed threshold definitions that were calibrated against a historical distribution that no longer describes where the current forecast is sitting, fails to communicate that shift in a way that is useful for people who need to act on it. This is where risk framing and probability framing diverge, and the divergence matters enormously for anyone whose job involves making decisions under uncertainty rather than simply describing it. Probability framing asks, how likely is a specific outcome? It is the language of scientific communication, of ensemble statistics, of institutional forecast products. It is precise, it is technically rigorous, and it is the appropriate language for describing uncertainty in a research context. When a climate scientist says 25% probability of Super El Niño, they are making a correct and defensible statement about the fraction of ensemble members that exceed a defined threshold. Risk framing asks something different. It asks, what is the range of outcomes I need to prepare for, and what is the worst credible case within that range? It is the language of emergency management, of agricultural planning, of infrastructure resilience, of the decisions that governments and utilities and aid organisations and farming communities need to make months before a climate event peaks. And for those decisions, the most important number is not the probability of the extreme outcome, it is the floor, the minimum plausible outcome, the thing you can count on even if everything goes better than the median projects. In the current ENSO forecast, that risk framing produces a very different picture than the probability framing does. The best case, the scenario where the spring predictability barrier introduces significant downward noise, where the atmospheric forcing weakens, where the warm bias correction brings the verified peak well below the current median, is still a strong El Niño causing significant regional disruption across the Indo-Pacific, drought stress across South and Southeast Asia, rainfall anomalies across the Americas, and global temperature pressure that will be felt in the statistics for years. That is the good news scenario. The central case is an event that meets or exceeds the strongest El Niños in the modern instrumental record, an event that the CFSV2 had to redraw its chart to display. An event that sits, by median forecast, at a level approximately equal to the conventional reconstruction of the 1877-78 event, the one whose consequences we described earlier in this video. The worst case is something for which the historical record provides genuinely inadequate precedent. An event in the upper tail of the current ensemble distribution, amplified by the nonlinear feedbacks that a record-warm Pacific and an elevated background mean state could produce, peaking at a level that would require not just a new chart ceiling, but a new vocabulary for describing what El Niño is capable of. All three of those scenarios are physically plausible. None of them is the scenario where nothing significant happens, because the subsurface heat content has already foreclosed that possibility. The uncertainty is not about whether an extreme event occurs. The uncertainty is about how far above the historical record it goes, and which point in that range the verified peak lands. We are debating how extreme, not whether it happens, and that reframing, from probability to risk, from how likely is the worst case to how extreme is the guaranteed minimum, is the single most important conceptual shift that honest public engagement with this data can offer right now, because it tells the people who need to prepare something that the probability statement, technically correct as it is, does not tell them clearly. The floor of this event is already in record territory. The ceiling is unknown. And the distance between those 2 points is where the lives and livelihoods of hundreds of millions of people are going to be decided over the next 12 months. 25% probability of Super El Niño sounds like something that probably won't happen. A guaranteed minimum of one of the strongest events in modern history, with an unresolved upside, sounds like something you act on immediately. The data supporting both statements is identical. The difference is only in how you choose to frame what that data means, and right now, that choice is not academic. Part 18, 3 futures. Let's be direct about what the current data actually supports in terms of where this goes from here. Not certainties, not impossibilities. 3 distinct futures, each grounded in real physics, each with a different set of consequences for the planet, and each more uncomfortable than the one before it. Because here is the thing about genuine scientific uncertainty that public conversation almost always gets wrong. Uncertainty does not mean anything could happen. It does not mean the extreme outcome and the mild outcome are equally plausible. It means there is a defined range of physically grounded possibilities, and within that range, the question is which one the atmosphere and ocean choose to deliver over the coming months. Understanding that range, what anchors the bottom of it, what drives the top of it, and what each point along it actually means for the world, is the most useful thing this data can give you right now. So here are the 3 scenarios, all of them plausible, none of them the scenario where nothing happens. That scenario was closed off by the subsurface heat content already sitting in the equatorial Pacific, and no atmospheric development between now and December is going to reopen it. The first scenario is the conservative case. This is the outcome where the things that could go wrong for the forecast, in the downward direction, go wrong simultaneously and significantly. The spring predictability barrier, that well-documented window of reduced forecast skill in the April through June period, introduces substantial noise into the model output. The CFS-V2 warm bias, which has been characterized at plus 0.2 to plus 0.5 degrees of systematic overestimation, turns out to be operating at the higher end of that documented range. The atmospheric forcing, the westerly wind bursts driven by the Madden-Julian oscillation, the sustained pattern of winds that has been stacking Kelvin waves in the subsurface since December of 2025, becomes less favourable over the summer months. Perhaps the MJO shifts to a suppressed phase for an extended period. Perhaps the trade winds partially recover sooner than the current pattern suggests. The Kelvin wave stacking weakens. The continued atmospheric cooperation that would push this event from strong to record-breaking fails to materialise. Under this scenario, the El Niño peaks somewhere in the plus 2 to plus 2.3 degree ONI range. And I want to be very deliberate about how I describe that outcome, because there is a strong temptation to call it the not that bad scenario, and that framing would be badly wrong. Plus 2 to plus 2.3 degrees on the ONI is comparable to, or slightly exceeding, the 1997 to 98 and 2015 to 16 events. The events that for nearly 3 decades have defined the upper boundary of what a super El Niño looks like. The events associated with catastrophic flooding across California and the American Southwest, fishery collapse along the South American coast, severe drought across Indonesia and the Philippines, monsoon disruption across South Asia, and a global temperature spike that set records for its respective year. That is the conservative scenario. That is what things going better than expected looks like in the current forecast. Not mild disruption, not manageable inconvenience, an event comparable to the strongest in the modern instrumental record, happening on a background mean state that is warmer than it was during either of those previous benchmarks, which means the absolute impacts will exceed what the same ONI value produced in 97 or 2015, even if the anomaly number itself is similar. The regional picture under the conservative case: severe drought across Indonesia, Australia's north, and the maritime continent. Drought stress across parts of southern Africa and South Asia, with significant risk to agricultural production in regions that are already operating with depleted water reserves from consecutive stress seasons. Rainfall anomalies across the Americas, with flood risk in coastal Peru and Ecuador and parts of the southern United States. Global temperature records for 2026 or 2027, either tied or marginally exceeded, depending on the timing of the peak. A substantial carbon cycle response as tropical forests come under drought stress and fire risk increases across the Amazon and Indonesian peat regions. This is not the nothing to worry about scenario. This is the extremely bad but within historical bounds scenario, the floor, the minimum, the case where almost everything breaks in the favourable direction for the forecast, and you still end up with one of the most impactful climate events of the past 30 years. The second scenario is the central case. This is roughly what the current model median is showing. The outcome that the ensemble is clustering around, the number that appears when you take the middle of the CFS-V2 plume after NOAA had to extend its y-axis to display it. The El Niño peaks in the plus 2.5 to plus 3 degree ONI range, most likely reaching that peak sometime in late 2026 or early 2027, depending on the precise development timeline. At plus 2.5 to plus 3 degrees, this event is definitively the strongest El Niño in the modern instrumental record, not tied with the previous leaders, not marginally above them, definitively beyond them, in a way that would require the scientific community to revise how the category of super El Niño is defined and what the upper bound of observed ENSO behaviour looks like. In terms of raw ONI magnitude, this scenario places the event in the same neighbourhood as the conventional reconstruction of the 1877-78 event, the Great Drought, the one that failed monsoons across 3 continents simultaneously. Whether it equals or exceeds that reconstruction depends on exactly where the peak lands within the plus 2.5 to plus 3 range, and on the reconstruction uncertainty that makes precise comparison to the pre-instrumental record inherently difficult. The consequences in this scenario move beyond what historical analogues can fully describe. Global temperature records broken by a significant margin, most likely producing the warmest year in the instrumental record in 2027, as the peak El Niño signal propagates into atmospheric temperatures with its characteristic 6 to 12-month lag. Monsoon disruption across South Asia at a level that would represent not just a single bad agricultural year, but a multi-year drought risk for water systems and farming communities that are already under stress from the elevated background temperatures of the past decade. Drought and fire risk across tropical forest regions, the Amazon, the Congo Basin, the Indonesian archipelago, at a scale with direct implications for the global carbon cycle, potentially reversing the absorptive capacity of ecosystems that are supposed to be drawing carbon out of the atmosphere, not emitting it. Coral bleaching at global scale exceeding the events of 2015 to 16 and 2023, which were themselves the most damaging bleaching episodes in the history of reef science. This scenario describes a world in which the chart that broke on May 1st was not an anomaly in the model. It was an early signal, the first visible indication that the climate system was preparing to deliver something that the instruments were barely able to measure and the language was not yet equipped to describe. A signal that the system then went ahead and delivered, fully, without revision, without the seasonal softening that the spring predictability barrier sometimes provides. In this scenario, the chart extension turns out to have been the most honest communication of the situation that any institution produced in the entire lead-up period. The third scenario is the aggressive case. This is the upper tail, the outcome that lives in the ensemble members running toward plus 3.5 degrees and beyond, the ones that pushed the CFS V2 display range past its previous ceiling, and forced the y-axis to be redrawn in the first place. It is the scenario that standard probability framing assigns low odds to, and that physical reasoning cannot dismiss. In this scenario, the atmospheric forcing does not weaken over the summer. It continues. The MJO remains in phases favourable to westerly windburst activity. The Kelvin wave stacking that has been building since December of 2025 persists and amplifies rather than dissipates. And crucially, this is the part that distinguishes the aggressive case from simply a stronger version of the central case. The nonlinear feedbacks between a record-warm Pacific and an already elevated background mean state begin to operate in ways that current models, calibrated against a cooler historical climate, are not fully equipped to simulate. The atmosphere's response to a given sea surface temperature anomaly scales with absolute temperature, not just relative anomaly. At higher absolute temperatures, the same degree of Pacific warming drives stronger atmospheric circulation responses, which feed back into the ocean coupling, which can amplify the ENSO signal further in a self-reinforcing loop that standard model parameterizations may be underestimating. The peak ONI in this scenario exceeds anything in the historical record by a margin that is not subtle. It forces a categorical revision of how Super El Niño is defined. It produces regional impacts that are, by definition, outside the range of what human observation has ever documented for an ENSO event, which means we cannot describe them with the confidence that historical analogues provide. We can infer them from the physics, we can model them from regional climate projections, but we cannot point to a previous event and say, it will be like that, but more. There is no previous event in this range. In this scenario, the language gap we have been discussing throughout this video is not merely a communication challenge between institutions and the public. It becomes something more significant than that. It becomes evidence, visible, documented, undeniable evidence that the physical climate system has moved beyond the range for which the scientific communication frameworks built over the past 60 years were designed. That the chart extension was not just a display adjustment, it was a boundary marker. The moment the instruments told us that the old map no longer covered the territory we were entering. All three of these futures are plausible. All three are grounded in the current observational data. None of them is the scenario where the subsurface heat content quietly dissipates, and December 2026 looks like an ordinary month in the equatorial Pacific. That scenario does not exist in the physics of the current situation. What all three share is more important than what separates them. All three represent an El Niño developing on a warmer planet than any previous El Niño in the instrumental record has ever operated on. All three represent an event whose forecast forced a model to redraw its own chart. All three are the consequence of a physical climate system that has accumulated enough thermal energy in the equatorial Pacific subsurface to produce outcomes that 30 years of operational forecasting history had never previously needed to display. The question is not whether something extraordinary is coming. The question is which of these three futures we're going to be documenting and explaining when the data from late 2026 and early 2027 comes in. Part 19. The final hook. Return to the chart. On May 1st, 2026, a Friday, a routine forecast update from NOAA produced something that wasn't routine. Nobody announced it. Nobody held a briefing. A chart that has quietly tracked the Pacific Ocean's behaviour through every major El Niño event since the system went operational. Through 1997 through 2015, through every warm pulse and cold reversal the Pacific has thrown at it, across 3 decades of continuous operation, extended its y-axis upward, not for aesthetic reasons, not because a designer decided the graph needed more visual breathing room, because the ensemble members were climbing toward values that exceeded what the chart had been built to show, and there was simply no other option. You either extend the axis or you lose the data, and you don't lose the data. That y-axis extension is, on its face, a small thing. It is a display adjustment, a formatting change. It added no heat to the equatorial Pacific. It accelerated no Kelvin waves. It changed nothing about the atmospheric circulation patterns currently building toward what may be one of the most significant climate events in the modern instrumental record. If you pulled up that chart on May 1st without any context, without knowing what the previous range had been, you might not even notice that anything unusual had happened. It would just look like a forecast plume, lines spreading forward in time, an ensemble doing what ensembles do. But formatting changes do not happen for no reason. And the reason this one happened is the entire story we have spent this video building toward. Every piece of physics, every observational data point, every structural tension between what the instruments are measuring and what the institutions are saying. The reason the y-axis moved is sitting 300 meters below the surface of the Pacific Ocean, in the form of subsurface heat content that surpasses every April measurement in the satellite era. It is moving eastward in the form of multiple stacked downwelling Kelvin waves propagating along a thermocline loaded with thermal energy at depths and magnitudes that have no modern precedent. It is compressed into a developmental timeline that is running months faster than historical analogues would predict. It is elevated by a background mean state that greenhouse warming and the inadvertent removal of a shipping industry aerosol have pushed higher than any previous El Niño in the instrumental record has ever operated against. And it is confirmed from multiple independent directions by a multi-model consensus pointing toward an event that sits at or above the magnitude of every documented El Niño in the modern record. All of that is what made the y-axis move. All of that is what lives behind what looked, on the surface, like a routine chart update on a Friday morning in May. And then there is the language. This is the other half of the story. The half that is harder to quantify, but just as important to understand. The careful probabilistic framing. The premature from the Met Office and the possibly unprecedented from the World Meteorological Organization, and the probability distributions that assign 25% odds to an outcome that the central tendency of the model data is pointing at directly. Throughout this video, we have been careful not to dismiss that language as dishonest or evasive, and we're going to remain careful about that now, at the end, because the dismissal would be wrong and it would miss the actual point. That language is the product of institutions that have calibrated their communication against decades of hard-won experience with forecast uncertainty that turned out to be real and consequential, experience with false positives, events that were called extreme and verified moderate, damaging the credibility of the agencies that made those calls in ways that reverberated through their institutional culture for years afterward. Experience with the asymmetric reputational costs of being wrong in the direction of alarm versus being wrong in the direction of caution. That calibration is genuine. The uncertainty it acknowledges is real. The professional judgment behind it has been earned through precisely the kind of difficult, public, high-stakes forecasting that most of us will never have to do. But there is a specific failure mode that even well-calibrated systems are vulnerable to, and it is this. Calibration becomes miscalibration, when the physical system changes faster than the calibration framework can track, when the range of outcomes that the framework was built to communicate about shifts in a way that the framework's internal norms were not designed to accommodate, when the chart that was adequate for 3 decades of El Niño history suddenly needs a new ceiling, and the language that was adequate for 3 decades of El Niño communication hasn't yet been given permission to build one. That is the situation on May 1st, 2026. Not a failure of science, not a failure of the scientists, a structural mismatch between the speed at which the physical climate system is moving and the speed at which the institutional frameworks built to describe it are able to adapt. The chart got extended in an afternoon. The language will take longer. Let's be clear about what did and did not fail here, because the distinction matters for everything that comes after this moment. The chart didn't fail. It was extended. That is not failure. That is a system working exactly as it should, making room for data that exceeds its previous range rather than clipping it or discarding it, or pretending it doesn't exist. The extension is the chart doing its job correctly in a situation its designers did not anticipate. The models didn't fail. They told us something. They ingested the observational data from the TAO buoy array, from the Argo floats, from the satellite sea surface temperature measurements, from the GODAS assimilation system. All of that real, measured, instrument-verified information about the actual state of the equatorial Pacific, and they ran the physics forward and they reported what the equations produced. That the output exceeded the previous display range is not a model failure. It is a model success that happens to be deeply uncomfortable. The scientists didn't fail. They are doing exactly what rigorous scientific practice requires, maintaining the epistemic standards that make their communication trustworthy over the long run, applying the uncertainty quantification that prevents premature conclusions from corrupting the forecast record, resisting the pressure to state more than the evidence, at this specific moment in the forecast cycle, firmly supports. If you want scientific communication you can rely on across decades and across events, you need scientists who maintain these standards even when the data is pulling hard toward a dramatic conclusion, especially then. What has happened is something more subtle and more significant than any of those individual failures would be. Something has shifted in the relationship between the physical reality of the equatorial Pacific Ocean and the institutional framework that human civilization has built to monitor, forecast, and communicate about it. The physical reality has moved further and faster than the framework expected, not because the framework is broken, because the climate is doing something the framework was not built to track. The chart had to be extended because no one had drawn the axis that high before, and no one had drawn it that high before because no one had needed to. The entire operational history of the CFS-V2, every El Niño season it has run through since the 1990s, every ensemble plume it has produced, every forecast update it has delivered, had fit within the previous range, until May 1st, 2026, when the data made that range obsolete in a single update cycle. What this means going forward is a question that extends well beyond the specific question of how strong this El Niño turns out to be. It is a question about adequacy, about whether the climate monitoring and forecasting and communication infrastructure that human civilization has constructed over the past 60 years, the buoy arrays and the satellite systems and the ensemble models and the institutional probability frameworks and the language norms and the press release templates, is adequate for the climate events that civilization now has to navigate, not the climate events of the past 60 years, the ones coming in the next 60. It is a question about whether the language of probabilistic caution, developed and refined in an era when genuinely extreme climate events were statistically rare, remains the right language for a world where what used to be extreme is migrating toward the center of the distribution, where the upper tail of yesterday becomes the median of tomorrow, where the chart ceiling of the previous forecast cycle becomes the floor of the next one. It is a question about whether the gap between what the data shows and what the institutions are willing to say is going to narrow, because the physical system stabilizes, because the current event turns out to be within historical bounds after all, because the spring predictability barrier delivers the downward noise that makes the conservative scenario the verified one, or whether that gap is going to widen, because the data keeps moving faster than the frameworks built to describe it can follow. The equatorial Pacific right now holds the highest April subsurface heat content ever recorded in the satellite era. That heat is not staying where it is moving toward the surface. It will warm the ocean. It will alter the atmospheric circulation across the planet in ways that will affect rainfall patterns in India, drought conditions in Indonesia, fire risk across the Amazon basin, coral reef survival across the tropics, global temperature statistics for years to come, and the carbon cycle feedbacks that connect all of those consequences to each other and to the pace of the climate change that is driving the background state elevation in the first place. None of that is uncertain. None of that is in question. The only question, the one that the three scenarios laid out earlier represent, the one that the spring and summer of 2026 will begin to answer, is how far. And the chart that Noah had to redraw on a Friday in May had to be redrawn because how far now requires more room than anyone had previously thought to build into the display. The system may now be producing events that our models and our language and our institutions and our infrastructure and our collective imagination of what climate extremes look like were not built to handle. That is not a comfortable place to end, but it is where the data leaves us, and the data, unlike the language, doesn't hedge.